This section on work, as you know, has got at least three different sorts of examples that we need to cover. So just a brief recap to start with. Work is an entirely new idea that we haven't encountered before in calculus, and it's defined to be what happens when you apply a force and you move something through a distance. So work is force times distance. That's the definition from physics. And this assumes that both the force and the distance are constants. So here's a very basic high school math example. If you were to lift a 2-pound book, you need to apply 2 pounds of force to lift it. All right, so you're applying 2 pounds of force if you're lifting it, and you lift it from a desk to a shelf 3 feet above the desk. So you lifted it through 3 feet. So how much work did you do? You had to apply 2 pounds of force, you applied it through 3 feet of distance, and so 2 pounds times 3 feet, you did 6 foot-pounds of work when you did that. This is not a calculus question, this is just getting the idea of work established. That's how work is calculated. We did mention that when you do the problems in metric, they will give you stuff in kilograms. That needs to be converted to a force. In the imperial system, pounds are already a measure of force, but in the metric system, kilograms are not a measure of force, they're a measure of mass. So to make that conversion, you need to use Newton's second law. You need to multiply the mass by acceleration due to gravity, which is 9.8. So you always have to do this. That's where that 19.6 newtons came from. It was the 9.8 times the 2 kilograms. Other than that, these are done the same way. It's just that initial conversion that has to be added. All right, so let's now do our first problem, our first new problem. And I'm going to do a spring problem to start with. Before we can do spring problems, we need to know about this thing called Hooke's law. All right, so Hooke's law is a basic physics principle, and it says this. The force that it takes to stretch a spring is proportional to the amount that you stretch it. Okay, now this is not talking about the length of the spring. This is talking about the amount that you stretch the spring by. That's not the same as its natural length. You will see natural length being referred to in this chapter. Natural length of the spring is the spring, its length if you didn't apply any force to it. If you just flopped the spring down on the desk, you didn't pull on it at all, that's its natural length. So say a spring had a natural length of 10 centimeters, and you stretched it until it was 15 centimeters long. How much did you stretch it by? From 10, stretched it out to 15 centimeters long. How much did you stretch it by?
5.
Yes, 5. From 10 to 15 is a stretch of 5. That's the stretch. That's what's being referred to when it says stretching the spring. It's not the length of the spring, it's the stretch of the spring that Hooke's talking about. Now, however much force it took me to stretch it to 5 centimeters, guess how, sorry, to 15 centimeters, how much do you think it would take to stretch it to 20 centimeters, comparatively speaking? To stretch it to 15, how much stretch was that?
5.
You just told me 5. To stretch it to 20, how much stretch is that?
10.
10. From 5 to 10, isn't that twice as much? So that would have taken twice as much force. To stretch it from 10 to 15 versus to stretch it from 10 to 20, it would take twice as much force to stretch it to 20, because the amount of stretch is doubled. It's doubled from a 5 centimeter stretch to a 10 centimeter stretch. Does that make sense? That's what Hooke says. The force it takes to stretch it is proportional to the amount you stretch it. If you stretch it to twice as much, it'll take twice as much force. If you stretched it to 3 times as much stretch, it would take 3 times as much force. That's Hooke's law. All right, now a problem. So a spring with a natural length of 12 inches is stretched to a length of 15 inches by a force of 6 pounds. Now, so far, that is not a physics question. It'll be useful information. We'll use it. The question, here's the calculus question. How much work is done to stretch it from its natural length, in other words, 12 inches, to a length of 18 inches? So there's the calculus question. There's the work question. But before we can answer that question, we first need to figure out the formula that governs the force stretch relationship of this spring. So let me get that figured out ahead of time. First, let's choose some variable names. Let's let x represent the stretch? Again, that's not the length of the spring, that's not how long it is, that's how far it went beyond its natural length. Let's let F represent the force. Now, using these variable names, Hooke's law can be written in symbols rather than just saying it in words. It says the force stretching a spring, so that's F, is equals proportional to, so that's a constant times, if something's proportional to something else, it's a constant times the other thing. So the force is proportional to the amount of stretch by. Well, we've given a name to that, we're calling it x. So it's a very simple formula. The force is a constant times the stretch. Okay. Now the thing is, the constant varies from one problem to another. It depends on the spring. And you can figure out that constant if they give you enough information about a spring that is being stretched by a certain amount of force. And that's exactly what they did here. It says this particular spring, it has a natural length of 12, but it's stretched to a length of 15 by a force of 6 pounds. Now, to go from 12 inches to 15 inches, take those two facts together, and what's the stretch that they're talking about here? Natural length of 12, stretched to a length of 15. How much did it get stretched by?
3.
Yeah, 3 inches. All right, so this stretch here is 3 inches in this particular instance. All right, and how much force did it take to do that? By a force of 6 pounds. So this is 6 pounds. Does that make sense, everybody? Okay, now plug those in. Remember, this is a constant. It doesn't, any pair of these that goes in there, that constant remains constant. So I'm going to plug these in, and I'm going to figure out what k is. So I know that 6 is equal to k times 3, which means that 2, actually let me keep my units here. This was pounds, this was inches. And so if I divide both sides by 3 inches, if I divide by this on both sides, I'm going to get 6 pounds divided by 3 inches. That's k. And obviously that does reduce down to a 2, and it tells me what k is. This is called the spring constant, and this particular spring has a spring constant of 2 pounds per inch. You okay so far with this? Now we can take that number, that 2, and we can put it back in here for k, and we have now a formula for the force-stretch relationship for this particular spring. This spring has a force-stretch relationship of 2x. Now that's not the question they asked us, but that's going to be proving to be very useful as we advance through this problem. So, to start with, are there any questions about how I got this? They gave us enough information here. We knew it stretched by 3 inches with a 6-pound force. Therefore, we can figure out what the k is for this fx relationship. F must be 2x. Now, the calculus part of the problem. All right, so reading that back again, let me move this down a little bit. It says, how much work is done to stretch it from its natural length to a length of 18 inches? Now I'm going to draw a picture here of what's going on, trying to visualize this relationship. So let's say that that's a wall. Let's say that this is just some reference axis, and here is our spring. It's attached to the wall at one end. And let's say that this is a handle that we're grabbing hold of to pull on it. So we're yanking on this, and we're going to start pulling that to the right. Let's say that right now it's at its natural length. All right, so this is the x-axis, and the x-axis does not represent the length of the spring, The x-axis represents what again? What did we say x stood for? It's still there on the screen.
Stretch.
Yeah.
Force.
The x stands for the stretch. X is how much it's stretched by. Okay. So right now, this spring is not being pulled on. This is a normal length, natural length spring. Therefore, how much stretch is it? What's x right now?
0.
Yeah, it's 0. Exactly. Now, according to the question, it says how much work is done to stretch it from its natural length to a length of 18 inches. Okay. Now, what was its natural length again?
12.
Yeah, 12 inches. We're going to stretch it to 18 inches. So how much will it have stretched by the time we're done? It has a natural length of 12, and we want to stretch it to a length of 18. How much will it have stretched by?
Oh, it's 6?
Yeah, it will have stretched by 6 inches. That's our target. We need to stretch it to that distance. So we're going to start with no stretch, and by the time we're done, we're going to be over here with a stretch of 6 inches. You okay? Everyone visualize that? Now, the trouble with that, and it sounds like we're getting a little bit of feedback here. Who's got 2 lectures going at the same time? All right, that's a little better. Okay, if we lost my train of thought here now. If we only pull this out a little bit, it won't take very much force. If we just yank on it just a little, just maybe stretch it by 1/2 inch, it won't take much force to pull it that far. If we want to pull it 3 inches, we already know how much that's going to take. That's going to take 6 pounds of force, right? But by the time we get out to 6 inches, how much force will it be requiring at that point? How many pounds of force am I going to have to be applying out here to keep it at a 6-inch stretch?
12.
Yeah. Everyone okay with that? Because the force is always double the stretch. That's what this F equals 2x says, right, in this particular case. For this particular spring, to stretch it by 6 inches is going to take 2 times 6, or 12 pounds of force to achieve that. So at this end, it takes no force to keep it at that length, because that's its natural length. By the time you get out to here, it's going to take 12 pounds of force to keep it stretched that length. So the amount of force keeps increasing the entire time. It keeps requiring more and more and more force the further we stretch it. And that's why we cannot use this formula. Because what does it say right here about force and distance? It assumes what?
The constant.
Yes, it assumes they're constants. The force and the distance are constants. But the more you stretch this, the more force it requires. Therefore, the force is not constant. You cannot do this problem using that formula, at least not directly. And this is where the calculus comes to help. And here's the logic. We say something like this. We say, okay, the force unfortunately varies as we move this further and further to the right. The force gets bigger and bigger and bigger. So let's take this interval of stretching, the stretch of 0 up to the stretch of 6, and let's chop it into thousands of tiny subintervals. Now I'm going to pick a specific subinterval, but it's a generic one. So there's a little tiny chunk of the stretch. I'm going to say that's happening at x, and I'm going to call this amount of stretch dx. So I'm right at x, and I'm going to stretch it a little bit beyond x. Let me zoom in so you can see this better. I'm going to stretch it by dx, up from x. Now, as long as dx is incredibly small, which I'm implying it is because I said I chopped this interval into hundreds or even thousands of subintervals, as long as you think of dx as being a tiny, tiny amount of extra tug, how much will the force change by as it travels across this little red interval? We know the force gets bigger from one end to the other, but how much bigger will it get? Will it get a lot bigger, the force? Or will it only change a tiny amount?
tiny amount?
Yeah, because we've only stretched it a tiny bit. We've only stretched it a little bit further from x up to x plus dx. It only went up by a very small amount of stretch, and therefore the force will only have changed slightly. And so we're going to pretend, as we do this stretching, as we stretch it from here up to here, we're going to pretend that the force on this entire little red interval doesn't change, but it stays the same throughout that short interval. All right, so at the x end of the interval, what's the force? It's 2x. At the right-hand end of the interval, it's actually changed up to what? It would be f of, what would an x now be at the other end of the interval? What's x here at that end of the interval? This is dx, that's x, so what's this other x value here? If I've gone from x and I've gone up by dx, what am I now at?
X dx?
X plus dx, yes. It's grown by dx. So at this end of the interval, the force would be 2x. What would it be at this end of the interval, the force? What would it now be at this end? Since we're now here, what would the force be at that end?
2x plus df?
Yeah, 2 times x plus dx, it would be that. All right, so the force will have grown. You'll be applying 2x pounds of force at this end. You'll be applying 2 times x plus dx pounds of force at that end. But we're going to pretend that it doesn't change. We're going to pretend that dx is so short that it really didn't grow by much. This is close to 0, we're going to note. This is close to 0. It's not a very large number, dx. It's close to 0. So we're going to pretend that f stays the same on this tiny interval. We're going to pretend that it didn't go up at all. Now, if it didn't go up, we're going to pretend that it stays at what value the whole time? We're going to pretend that it stays at 2x the whole time. All right, so if it stays that much the whole time, let's now figure out the amount of work we did as we went across this little red interval. I'm going to call this dw. W here is standing for work. Now, we want to find W for the entire stretch from 0 to 6, but right now I'm not worried about that. I'm focusing on the little portion of the whole process, the little red bit. As I stretched it from x up to x plus dx, we know that the work is going to be the force that we were applying multiplied by the distance through which we applied that work. But what are we going to pretend, did we say, that the force was over this entire tiny interval? We said it would stay at the same amount of 2x the whole time. It doesn't really. It really, by the time you've reached the right-hand edge of the red interval, by the time you've reached this right-hand edge, it's gone up to 2 times x plus dx. But we know that dx is very tiny. So if dx is very tiny, say let's call it 0, this really is still 2x. So we're going to pretend the force is 2x the whole time. And what's the distance that we moved through as we stretched across the red interval?
6?
No, just the red bit. Just the red.
X plus dx.
Well, to get from x to x plus dx, how far did you go?
dx.
Yeah, just dx.
Oh, dx.
Yeah. The width of the interval is only dx, so that's how much distance you traveled to get from this edge of the red to this edge of the red. You only went through a distance of dx. All right? Now we know this isn't really true. We know it's not really 2x the whole time, but we're giving ourselves an excuse to use this formula, which requires, again, that both of these be constants, right? So we're acting like the force did not vary, that it stayed 2x the whole time, that it didn't go up as we went from left to right edge of the interval. We're acting like that's now being treated as a constant. Dx, of course, is just the width of the interval. That's not variable. That's just a constant dx. So now we get away with using this formula that has that restriction on it. We can now get away with it. All right, so plugging those in, that gives us dw, the amount of work we did for the little red stretch. And dw is just going to be 2x dx. Okay? Now, that was just one portion of the work. We want all the work. So how can you turn a dw into a w?
Integral that?
Yes, integral. You integrate it. So we integrate this, and we get w. And we integrate this, and we get the integral of 2x dx. And what does x vary between?
0, 6?
Yes, 0 and 6. It varies from 0 to 6. And it's a very easy integral, of course. You get to get x squared from 0 to 6. And that would give you 6 squared minus 0 squared, which is 36. Now, units. Remember that in this particular instance, rather than what we used when we were introducing the idea, we use pounds and feet. We are using pounds and what?
Pound and inch?
Yeah, pounds and inches. So instead of this having units of foot-pounds, this has units of inch-pounds. Now, that's a rather unusual unit. You don't usually see people discussing work in terms of inch-pounds. So we probably should convert it to its proper value. What is an inch if you rewrite it in feet? How many feet is an inch? Isn't that 1/12 of a foot? Right? Come on, guys. An inch is 1/12 of a foot, isn't it? So this is 36 times 1/12 foot-pounds. And of course, you can cancel that. You can cancel the 12 into the 36 and get 3. So now we have 3 foot-pounds of work. And that's it. That's how much work it took to do that stretch. It took 3 foot-pounds of work to stretch it from 0 to 6 inches beyond its natural length. All right? Any questions about what we've just done? Now, if you want to think about it, this is kind of similar to how we very first invented integrals. And we were finding areas under these swirly curves, and we took the interval and we said, we don't know how to find the area under a curve, but we do know how to find the area under a rectangle. So remember how we sliced the interval into lots of little short intervals? And then what did we pretend the top of each of those intervals was? On the old rectangles. Didn't we pretend it was flat? Remember doing these, guys? Come on. The old days we used to have integrals like this. We sliced them up into subintervals, but then when we did the tops, didn't we pretend they were flat tops, like that? That's what we've just done here with this force. We know this force keeps on getting greater and greater, but on each little subinterval, we are going to pretend that it's constant, just like we pretended the top of this rectangle was constant when it really was curved, and the top of this thing was constant when it was really curved. Remember how we perfected that because we made them so skinny that eventually it became a perfect answer? That's the same deal here. We make eventually dx become so tiny that pretending this is constant becomes irrelevant. And that's what the whole integration process is about. Yes?
Excuse me, Professor Barker, the connection is so slow and the screen is blurry and we can't hear you.
Uh-oh. It sounds like we've got a very... if you're all experiencing it, it's got to be at my end, and I don't know what to do about it.
Yeah, me too.
So, I don't know what I can do about it. I'm on my fastest network here. Whew. I had an internet outage here yesterday. Completely took me out for 4 hours. And I don't know it's never really come up to full speed again. I'm not sure what I can do about it, guys. I will be posting this recording. That's all I can offer you. And I am capturing this in high definition on my own computer. And I will be posting that up to Canvas later today. So if you If you have a blurry connection right now, you can watch it in better definition later. That's about all I can offer, I'm afraid.
Okay, thank you.
I'm sorry. I'll also be posting the notes, of course, as I always do, and those you'll be able to read better once you see them as a PDF file, I'm sure. So I apologize, but I'm not sure what else I can do at this point. I could turn my modem. Has it gotten better again?
Yes.
Okay. Well, so it's fluctuating in its speed, apparently. Anyway,
yes.
we better forge ahead. Now, this is the first time you've done one of these, I realize, and it may seem a little hard, but basically these turn out to be quite simple. All you do with these is you figure out what the force is based on Hooke's law, and then you integrate that to get the work. Isn't that just the Hooke's law thing? 2x being integrated? That's all it is. And remember what these limits represent? What does the 0 represent? Is that the length of the spring? Is 0 the length of the spring? Come on, guys. It's not the length of the spring, it's the stretch of the spring. So it's being stretched by nothing to start with. It said stretched from its natural length to a length of 18 inches. Now its lateral length was what? 12 inches. So the amount of stretch at that point was 0, but once it reached 18 inches, it was now at a stretch of 6. So from 0 up to 6. Does that make sense to everybody now? So get the Hooke's law formula for force, integrate it, and it's from initial stretch to final stretch. That's it. That's all these take. All right? It's telling me again that my internet connection is unstable, so I apologize for that. All right, so I'm going to now move on to a much harder type of question. And this is going to be a fluid pumping problem. These you have to kind of take on a case-by-case basis. So let's take I think we'll only have time for one example of this. I'm looking at the clock here. So I'm going to do a basic one to start with. All right, so a cylindrical tank has a height of 20 feet.
Is he frozen?
Yes.
Am I frozen again? Oh, crap.
Soon.
Oh, here he is, I think.
This meeting is being recorded.
I'm back. Hopefully it's going to be better. I just told it to change my Wi-Fi network to one from a different part of the house. Hopefully that'll be better. Usually the other one I was on is better, but anyway, we'll see. All right, so a cylindrical tank has a height of 20 feet and a radius of 6 feet and is full of water. Water, and this is one thing you probably want to memorize because it comes up so often. Let me zoom out a little bit. Water's density. Water has a density, and your book uses a slightly incorrect number, but I think it uses it because it's an easier one to work with. It's 62.5 pounds per cubic foot. How much work is needed to pump all of the water over the upper rim of the tank? All right, so let me draw a picture of what's being described. So we have a cylindrical tank, and it's 20 feet deep. So let's say that this is 20 feet here. It's full of water, and we know that this is 20 feet. We know that its radius here, this distance here, is 6 feet. And we know that it's full. And we want to get all of the water up and out of the tank, according to the instructions. Now, the trouble we have with this is, depending on where you are in the tank, you're going to have to get moved a different amount. So the water at the very top of the tank barely has to move at all to get out of the tank. The water at the bottom of the tank has to move 20 feet to get out of the tank. And so the distance we're moving the water through varies depending on where we are in the tank. Now that gets us back to our work is force times distance business again, that said we need both of these to be constant. And this time, what is it that's varying from one portion of the tank to another? The distance varies. It varies from pumping fluids only by a fraction of an inch to pumping some fluid 20 feet. And stuff in the middle of the tank is being pumped through 10 feet. So the distance varies. Now what we do to overcome that, we again force that to become a constant by using slicing. So what I'm going to do is slice this horizontally, and I'll talk about why it's chosen this way in just a second. Let me get it drawn first. We take a very, very, very thin slice of the water. So there's my skinny, skinny slice. Now, it's so skinny that how much does the depth of the water vary within the slice? I'm not talking about up here or down here. I'm talking about just within the red slice of water. How much variability of depth is there? Would you say it's a lot of depth difference here? I already said it's a really, really skinny slice.
Almost zero?
It's almost zero. Yeah, there's barely any difference in depth here, right? Say the top of this slice is at a depth of 8 feet. The bottom of this slice is at a depth of 8 feet and 1/millionth of an inch. Well, it's practically flat then, isn't it? And therefore, all of the water in this slice, because it's so thin, all of the water in this slice is essentially at the same depth. And therefore, all of it can be treated as just like lifting the book in our initial example, right? We didn't have to worry about the fact that the bottom of the book is slightly lower than the top of the book. And we didn't take that into account at all, did we? Because, it's not a big deal. The same thing here. We think of this disc of water as essentially being like that book that we lifted up onto a shelf. We didn't have to use calculus anymore on the book. We wouldn't need calculus on this bit as long as it was super, super thin, really, really skinny. That's what we need here. All right, so I'm now going to introduce some coordinates. I'm going to introduce an axis, and I want you to get used to this because it does make the problems easier. It's going to be an upside down axis. Now, because it's vertical, I tend to call it a y-axis, although I am aware that your book tends to call it an x-axis. It's okay, you can call it anything you like as long as you give it a variable name, but I tend to call it y just because it's a vertical axis, and that's what we're kind of used to. And I would say that the place that the slice is happening at is generically called y. All right, now I will always set I shouldn't say always, I will usually set the top of the tank to be at a depth of 0. And therefore, what is the bottom of the tank at a depth of?
20?
Yeah, 20. Notice how this axis is an upside down axis. It's positive going downwards rather than our usual upwards. That just makes the math easier. Okay, and this won't be the last time we see an upside down y-axis. There are other types of problems we're going to do later where it's easier to think it that way as well. There will be exceptions to this, but for most problems this will make the work simpler if you do it this way up. The deal with these axes is you can pretty much do them any orientation you like, but some orientations make them simpler than others. I could put it with 0 at the bottom and the y pointing upwards, and that's possible. As long as you're consistent with your choice, that's the main thing. Once you've chosen it, stick with it. And how would I label this thickness here of this slice?
Delta V?
Delta
Sorry, Y.
Delta Y, yeah, delta Y. The thickness, not the volume, but the thickness of the slice. I would call delta Y, or I'll abbreviate, I'll kind of short circuit and I'll call it dy. Your book will call it delta Y. Absolutely, your book will call it delta Y. But we're going to kind of short circuit it in our work. So I'm going to call that dy. Now I'm going to now find the work it takes to lift that disc out of the tank. Now, in order to know how much work it takes, I need to know force times distance. The distance I already have tagged. The distance is y feet, isn't it? From 0 to y is y feet. That's the distance. The tricky part now is how much does it weigh? Well, to figure its weight, we can use the fact that water has a density of 62.5 pounds per cubic foot. Now, if 1 cubic feet weighs this much, I need to know how many total cubic feet this guy is. How many cubic feet is that disc? So I need to find its volume. And its volume is easy. After all, isn't that little red disc just a cylinder? So what's the volume of any cylinder? It's just pi r squared h, right? In this case, that would be pi times, and what's the radius of this disc?
6?
Yeah, pi times 6 squared. And what's the h? How tall is the disc? Not the tank, the disc.
Delta Y?
Yep, delta y or dy. So the volume of this is 36 pi dy. Okay, that's a stepping stone. I'm not trying to find the volume of the tank. I'm trying to find the volume purely so I can find how much it weighs. So now I use this number. I know that water weighs this much. So that's in pounds per cubic feet. This is in cubic feet, right? This is the volume. If I multiply that by 62.5 pounds per cubic foot, what will happen when you multiply cubic feet by pounds per cubic foot? What will you get?
You get the pound?
Yeah, you get the pounds. Exactly. So this will now be in pounds. Now, what is it that we measure in pounds? Not volume anymore, but force. Weight or force. Remember, when you're lifting things, force and weight are the same idea. They're the same thing as each other. So we now know the force required to lift this disc. Finally, work. Work is force times distance, right? So we are going to take this and multiply it by, let me grab my red pen here, how much distance it's moving through. How much distance does this have to be lifted through? Where is it at? It's at y, so how far is it from y to 0? It's y feet. So I now multiply that by y feet, and it converts from being force into being work. So multiply this by y, and you get 62.5 times 36 pi times y dy. Now remember, these were feet, those were pounds, so these are now foot-pounds. Okay? Now finally, I want all, that's the work for one disc, that's dw, one slice of work, but I want the work for the entire cylinder. So I need to add up all the works for all the slices. What do you have to do to a dw to get a w?
Integrate.
Yes, integrate it. And so we get work itself. Work is going to be the integral, and I can take these constants outside. It's the integral of y dy as y ranges between where and where? 0 and 20. Okay? Now, I'm out of time, I realize, but basically it's a fairly easy integral to do. I get 62.5 times 18 pi y squared from 0 to 20, which is 62.5 times 18 pi times 20 squared, minus 0, because if you put the lower limit in, you just get 0, and then it's just a calculator job. You can finish it from there, right? Question? Remember, the integral of y is 1/2 y squared. The 1/2 goes with the 36 and turns it into an 18. Integral of y is 1/2 y squared. Okay, any questions? And that would give you the total work. And what would it be measured in? Foot-pounds. Foot-pounds of work. This final answer is in foot-pounds when you finish it.